Hi, everyone. I'm just waiting maybe one more minute. We still have a few people joining, but it'll just be a minute here. Okay, we'll get started. First, just thank you so much for being here, taking time out of your day. I know, boy, with the COVID and everything going on, that you've probably seen a lot of these virtual things. So I really want to encourage you to. I see a chat here. Somebody asking me a question. You can't hear any audio? Can I ask if anybody else maybe could, through the chat, can you tell me if you can hear me, please? Everybody else seems loud and clear. So I think, Sean, that might be a problem at your end. Okay. I think that's just somebody with an issue at their end. So I'll keep going. Hopefully you can figure it out. Anyway, really thank you for your time, taking the time to be here. What I'm going to be discussing is clamp-on transit time and Doppler flow measurement technology, and really understanding the difference and when to apply which technology. And also, in some cases, you'll find that the two might be interchangeable. So without further ado, let's move on and go to our first slide here. Just a brief background. I've been involved in flow measurement for 25 plus years, anywhere from product design and development to testing, application engineering, global sales. I joined Grayline Instruments back in 2018 as a regional sales manager. So my background with Grayline was my first introduction into Doppler and Transit Time clamp-on technology. Since I've transitioned to central sales manager for Pulsar measurement, which really includes all products under the Pulsar umbrella. But my passion really is being in flow measurement has been with our transit time and our Doppler flow meters. Just a brief explanation on the difference between the two ultrasonic technologies, that's transit time and Doppler. And one thing I want to point out here is often we'll hear transit time referred to as ultrasonic technology and Doppler is just Doppler technology, but in reality, they're both ultrasonic. Both work on the same principle. An electronic pulse is fired to a crystal, and through that crystal, sound waves are fired through the pipe wall and into the process. So what happens after that is where they differ. So let's first look at the signal strength. And that's really the metric on how we determine how well the meter is working. In the case of transit time, though, the transit time should be at or near 100% if it's working properly, the transit time signal. And you will see that in signal strength. And when you align your transducers, and we'll show you how that's done in the next slide, you really want to see that 100% signal strength or close to it. And that will happen whether there's flow or not. So the signal strength remains constant from 0 to maximum flow. I can have nothing flowing in a pipe that's filled with liquid, and I'm still going to be, my two transducers are still going to be communicating with each other. So my signal strength should be 100%. With a Doppler meter, when I clamp on that single transducer, I'm not going to get any signal strength with no flow because it works on a different principle, and we will explain what that principle is. But the graph, or this chart you see at the bottom is a little redundant, but it shows you that from 0 flow to 100% flow, you should see 100% signal strength from transit time. Doppler, 0 flow, 0%, and then all the way up the scale, it can range from 20 to 100%. With a Doppler meter for great measurement, you don't need 100% signal strength. I've had success anywhere up between 20 and 100%. So generally my rule of thumb is when I fall below, say 20, 25%, I start to look at the measurement and say, is this really reading accurately? But typical signal strengths we see vary in that range. So here's a nice illustration of how the two work. You can see, look to the left first, and that is the Doppler meter. And what it's doing is it's what we call sending a continuous Doppler signal. So it's continuous Doppler technology. And it is firing sound waves through there at about 640 kilohertz. That was a tongue twister. And it's picking up on air bubbles, particulate, anything nasty flowing through that flow stream. It's targeting. And as that particulate accelerates and moves away, that Doppler signal is going to change. That's going to be an altered frequency. So it's coming, in the pipe at 640, but as it gets further and further away, it's returned at a different frequency. And that frequency, that difference is proportional to the flow rate. And you see, that can be air bubbles, that can be in slurries, it can be anything from rocks and sand, just about anything that flows through a pipe. So really set up for nasty applications and designed to target things flowing through the flow stream. So you can understand why then, if there's no flow, why we're not getting a return signal. It's because there's really no altered frequency. Transit time works differently. You can see it off to the right. We are bouncing a signal from one transducer to the other. And you can see where that could occur at 0 flow. What happens with transit time is as the flow increases, the upstream transducer, it will travel faster to the downstream transducer. And the downstream transducer is bouncing a signal back against the flow that works harder to reach that differential. So as those two signals communicating with each other, as the flow increases, the difference between the transit time from one to the other is proportional to the velocity. And eventually that's the flow rate. So everything is converted in the controller to a flow rate, but we are measuring velocity in both cases. So let's first look at the transit time. The two transducers that you mount on your pipe, the spacing is determined by pipe dimensions and process fluid. So really what you're entering in is your pipe size, material, your pipe wall thickness, inner diameter, and then whatever the process fluid is. This is important because it also calculates what the speed of sound is. So if I'm measuring, say, water versus some type of water glycol mixture or gasoline or something like that, it's going to have a different speed of sound. We also have a calculated speed of sound in the meter, so we can tell if the calculated speed of sound is similar to the actual speed of sound going through the pipe. So that's a diagnostic feature. One thing you'll notice, all our menus have this 4 push button control feature. Very, very easy to set up and operate. So in a case like our transit time meter, what you would do is enter your process conditions, process fluid, temperature, and also your pipe wall dimensions, and it's going to tell you what the transducer spacing should be, and that's how it's determined. Also, there's a diagnostic menu showing you signal strength and also the communication between the transducers. It'll tell you that it's working properly. And now in the TTFM 6.1, this is our transit time meter. We have 3 different types of configurations. By far the most common is the one to the far left. It's what we call our V mounting, also called a 2-cross. And in the meter menu, it will default to that. It'll automatically be a 2-cross. It provides flow averaging because you are taking a double path from one transducer to the other. The Z mounting you see in the center is sometimes used when we can't get good signal strength from the V mounting. That's also called a 1-cross, and reasons for not maybe getting the same type of signal strength from the V mounting would be if you have a very large pipe, for example, and it has a hard time making that deflection from the opposite pipe wall, then you want to take a more direct approach. Also, let's say maybe you have buildup or scale on the pipe wall that's making that bounce difficult. Then we would go to a Z mounting. It's actually the second choice if the 2-cross yields low signal strength. And that's one theme you'll hear with our transit time meter is we really gauge off of signal strength. That, let's say I put it on, I expect 100% signal strength. I'm getting 50. I don't like that. Something's wrong. And I don't think I'm going to get accurate measurements. So we have diagnostic tools that show you signal strength, and also show you some other metrics that we can use to determine whether we're getting an accurate signal or not. The Z mounting is mostly used on pipes greater than 30 inches. That statement is a little outdated. We have now introduced our new large pipe transducers, and I will talk about that in a little while here. But go to the W mounting to the far right. We also call that a 4-cross. And that's very common in very small pipes. And the reason it has to be done that way is because the pipe is so small and we're sending out these signals at about 1.2 megahertz. So it's hard for those transducers to process that signal quickly. So we do a double bounce. The good news there is you can see we're getting a lot of averaging because we've got actually 4 paths there that we're capturing through the flow stream. So that mounting on small pipes, and especially with our new small pipe transducers, is very, very accurate. Just a few notes here. Transit time application. Oops, sorry about that. Got away from it. Transit time. We'll talk about limitations and where it should be used. It's really designed for use in full pipe with what we call relatively clean fluids. It can have a little bit of stuff in there, whether that be particulate, maybe some aeration, but generally we want clean, non-aerated fluids. It's suitable for a wide range of pipe materials, sizes, and thicknesses. So, we're talking anywhere from PVC pipe to cast iron to stainless steel, a lot of different pipe materials. Another thing to keep in mind here in terms of cost and savings is that it doesn't matter whether it's on a 24-inch pipe or a 2-inch pipe, the cost is the same. Suitable for a wide range of process temperatures. We can run this from cryogenic, say down to minus 40 degrees, all the way up to 300 degrees. Sometimes we can go even a little bit higher if we use a special dielectric grease that can handle high temperatures. And what I'm referring to with the dielectric grease, that's the grease or the silicone gel we apply to the transducer before we mount it to the pipe. You see now what we have, and this is fairly recent, we have three transducer options. A couple of years ago, we only had one, and you had to really make it fit all applications. Now we have what we call a small, medium, and large pipe transducer set. You look to the upper right there, and that would be, say, a large pipe transducer. Down to the our B sensors are probably the most common. That is, a pipe range of anywhere from, say, 12 to 36 inches. And then our new small pipe transducers, these were a great new addition, because you can imagine a large transducer like you see on the top there, or down to the left, trying to fit the curvature of a small pipe. That was very difficult. With the new small pipe transducers, that's done very easily. And I think we're talking all the way down to a half inch, even sometimes down to quarter-inch pipes. So that is relatively new, along with our large pipe transducers. The difference in the large pipe transducers is that we can make that bounce that we're talking about with transit time across a much larger pipe, and be assured that it's going to reach the other transducer. Also, if you have viscous fluids or other fluids that are kind of hard to cut through with that sound, since it's set at a lower frequency than the small or the mid-pipe transducers, it's a lot easier to do. So even for some difficult applications that might be, say, on 12-inch pipes, we might recommend going to a lower frequency transducer, which is also our large pipe transducer. We'll just give a typical transit time application. This one here happens to be a frac water supply line. This is pretty clean water. It's being used to accurately measure the water that's being supplied. Also being used for leak detection, because sometimes these lines can go on for miles, and they want to see if anything's being lost between point A and point B. The result is that these are operating to customer satisfaction. And an example where two technologies can be used at the same site, we have a case where ended up using Doppler meters on raw crude lines, and they're working great. And both of these are in the same oil field. So I want to make sure I'm not missing any Q&As as we go along. I see, how do you determine positioning of sensors when clamping on the pipes? So that's just simply determined by pipe size, internal diameter, pipe wall, and also the process fluid. So what you would do, let's just take, for example, with that push button screen I showed you on the controller, you'd go to the menu, you'd go to the calibration menu, and you would enter in the pipe size and wall, you would enter in the fluid, you would enter in the temperature, and then it will tell you what the transducer spacing should be. It'll say it on the screen. So that's how it's determined. And you'll see in this example, that's probably looks to me like about an 8 to 10 inch pipe. The transducer spacing is a little wider apart. The smaller the pipe gets, the closer those transducers tend to move together. But that's all predetermined by entering information into the control box. And I'll show you a photo of that. And then after that, all you have to do is space the transducers accordingly. I hope that answered your question. Now let's take a look at the DFM 6.1, our Doppler flow meter. Very easy to install, because in this case, we're just using a single transducer. Again, same thing, wide variety of pipe sizes and materials. And with the Doppler, we tend to see a lot of different pipe sizes and materials, especially on the material side, where since we are dealing with nasty process fluids, I see anywhere from glass line to cement line to mortar line, all kinds of lining on pipes, epoxy lining. And we can still, since we're sending that signal at a low frequency, we can still penetrate that pipe wall and get into the process fluid and also have it returned. So it's really designed for nasty applications that can be abrasive, anything that abrasive or corrosive. Since we're not coming into the contact with the process fluid, we don't have to worry about that. Again, the clamp-on technology with a low frequency signal allows for penetration through thick-walled pipes and measurement of complex abrasive and corrosive fluids. No contact with the process. Also, portable models are available, and I should have said that about the transit time as well. We have portable versions, battery powered, and also both for the DFM, the Doppler, and the transit time. Our fixed models are also available in DC power as well. Take a look at what a typical Doppler application looks like. This is a large pipe. I believe this particular one here happened to be raw water, and it wasn't filtered, had a lot of stuff in it and a lot of aeration. But you can see single transducer installation, dirty, and you keep hearing me say the term aerated water and chemicals. Little secret about the Doppler meter is sometimes you can have clean water, but if it's at a low pressure, say below 20 PSI, that's not enough PSI to compress the air bubbles in it. So don't dismiss all clean water applications at lower pressures. Sometimes we can pick up air bubbles through there, and it's a nice convenient installation where you only have to use the single transducer. On higher pressure clean liquids, it wouldn't be recommended because all the micro bubbles, or what I would call targets for the Doppler meter, would be compressed, and you just would not get, it would show up basically as zero signal strength. Viscous liquids, sewage, produced oil, frac water, pulp and paper type applications like liquors and that type of thing. Dredging slurries, this is used a lot in dredging. Also for HDD mud, both in drilling, like where we're doing trenchless technology, where you're laying a pipe under the ground and you're pumping drilling fluid down there that's got a lot of stuff in it. And also the return drilling fluid contains a lot of, heck, it could be roots, dirt, anything, but that's perfect for the Doppler. Again, low pressure water, other liquids where air bubbles are not compressed. And it's a real economical measurement for larger pipe sizes. This is a typical example at a wastewater treatment plant where we see a lot of Doppler applications, whether it be waste activated sludge, return activated sludge, influent, some types of effluents. But this is a good example of, this is a mortar lined pipe. It's the original waste activated sludge from the primary clarifier headed to the digesters at a wastewater treatment plant. I actually installed this one myself. I got about 75% signal strength, which is fantastic for a Doppler meter. That happens to be a glass lined pipe. They originally tried mags and they got kind of eaten by the process. Then they tried competitors' transit time models, because a lot of times our competitors do not offer a Doppler meter. Most of them don't. And this fixed the problem. They were having issues with the signal dropping off with the transit time meters. It would just simply, they couldn't make that bounce because of all the junk going through the pipe. In this case, they installed our Doppler meter, and I saw the graph just the other day, and it was beautiful. It was tracking their calculated flow rate, the waste activated sludge to the digesters. It was tracking it within about 1.5%. That's really good measurement. The other big thing, obviously, is that we can install this with no interruptions. And to put in a mag meter here, which they tried at first, you have to cut the pipe and flange it. So very, very easy installation. And just remember this, a lot of applications for this at wastewater treatment plants. So brief summary here on the differences. With the transit time, we're talking a little bit higher pressure, and I mean that in terms of clean fluids, greater than 20 PSI. So where if it's a clean fluid that's compressed and we don't get those air bubbles, that's more than likely going to be transit time. Doppler, we can do it on lower pressure liquid applications. because there's likely to be some entrained air bubbles in there, or what we would call targets. General rule of thumb we say is use transit time with less than 2% undissolved gas or solids by volume. That's about 20,000 parts per million. Doppler, we like to see greater than 2% undissolved gas or solids by volume. I think to be safe, I would put that more in the 2 to 5% range, based on my experience. Transit time, another example, if the location is measurement downstream of strainers. So if there's, let's say you have a raw water line coming in and there aren't any strainers, there's no filtering or anything, that might be more for a Doppler. But if the water has been filtered or cleaned to a degree, that's going to be transit time. The size of solids and gases we're talking about here is about 100 microns, what we want to see with a Doppler meter. And you know, a little tip, one of our engineers added this was watch for clues about the application. You know, so, for example, stainless pipe generally means that it's probably a process flow that's clean. Also, air is a better reflector than solids. So don't hesitate to use it where you have aerated applications, even if there are little or no solids. You just put it in perspective. If I've got say a chunk of sand or dirt going through a water line, as opposed to an air bubble, the difference in density is much greater with that air bubble compared to the water than say the sand. So the air bubble actually makes great reflectors. I'm going to just pop up here. I see something in the chat here. Oh, this is one chiming in is one of our treasured representatives here. Okay. This would be AJ. Sorry, I'm going to scroll down here. Let me just start with some of these questions. On a TT flow meter, the distance between the sensors is in thousandths of an inch. Is it difficult? You know, the way I would answer that is I would say, you know, we do provide a spacer bar, but my experience has been, you know, even using just a tape measure, I believe there's a lot more room for error than you think. I think we're trying to get you to do it as perfect as possible. I don't know what the exact number is in terms of how far you can be off, but it doesn't literally have to be within thousandths of an inch. And I think this might be answered further down. It's time of flight, so if spacing is wrong, accuracy will be off. That's true. And spacing can be wrong and still get a good signal strength. And that came from AJ Weezy, who's one of our representatives who installed a lot of these meters. And I think he understands. Here's the thing, and the way to diagnose this is, and let me point something else out here too. Sometimes we don't always get the most accurate information on the internal pipe diameter, or sometimes the customer might say it's not lined when really there is a lining in there. Then you can move the transducers around until you can get that signal strength. It makes it a little more difficult, but if we get all the information up front and you measure that off correctly, use the spacer bar, a tape measure, generally we see you're going to get good signal strength right off the bat. So I hope that answers your question. So I wanted to leave plenty of time for more questions here. You know, and anything that I haven't covered you'd like to discuss or comment on? So make sure on my Q&As I'm catching everybody. Okay, I answered that question. Okay, that's good, really good questions here. How does corrosion on the pipe affect the reading? Really really good question. So really in two ways, and it really depends on the amount of corrosion. And let's look at both. Let's look at first of all, the external corrosion. Let's address that. So you walk up to a pipe and let's say it's got a lot of rust or it's got paint over the rust, and you're not getting like the desired signal strength either from the Doppler or the transit time. We would recommend you buffing that down. Okay, so maybe you could get down to the raw metal. It's not always required, but sometimes that's just a good practice. If you see a thick coat of paint and you're not getting the signal strength, or if you see a lot of corrosion, maybe buff that surface where the transducers are going to be mounted. In terms of internal corrosion, as you know, we can't see inside the pipe. So in terms of two ways, we'll talk about buildup too. It does slightly change the area, the internal area of the pipe. So in the equation, there might be a small error there. But as long as we really, like I said, the diagnostic tool is signal strength. So as long as I know, and I set up my transducers, and let's say I'm sending those sound waves through the pipe and through that corrosion on the inside of the pipe, and it's still reaching my other transducer, and still getting 100% signal strength, or in the case of the Doppler, within an acceptable range, I know it's really not having that big of an effect on my reading. Okay. Now, there could be cases where it's just so bad in there, there's so much buildup that you might have to move that transducer around to find an optimum location, because pipe doesn't corrode evenly externally or internally. So yes, can corrosion affect it? And I will say also that not as much as it used to. These kind of meters in the old days got kind of a bad reputation because maybe the signal strength wasn't strong enough, or the filtering wasn't good enough, or the diagnostics weren't good enough. So any type of corrosion would have an effect. There's some old pipes out there. The new generation of transit time and Doppler meters are designed to kind of handle that type of thing. So I just see another question pop up here. The difference between DFM 5.1 and flow pulse. Well, the flow pulse is, so you're obviously familiar with the Pulsar flow pulse. It's just different ways we're doing the Doppler technology. In the flow pulse is designed more to read flow or no flow. It's not designed to be perfectly accurate. That's not what you're looking for with the flow pulse. It's almost more like a flow switch, and I could go into great detail into the algorithms and filtering and signal processing and one type of Doppler technology versus another, but just know that one is intended to be within that 1% to 2% accuracy range, and the other, if I'm not mistaken, I believe there is not even an accuracy spec on the flow pulse. It'll just be reading, you'll get a signal, it'll be some representative of the flow rate to a degree, but it's more designed for flow, no flow situations. Whereas the DFM 6.1, the gray line legacy product, is more designed for accuracy. It says, good day. Regarding the last question, transit time should be better for a corroded pipe or Doppler. I think that's a tough one to answer. And the reason I say that is you got to throw the process fluid into the equation. If all things being equal, I would say there isn't much difference. I will say the Doppler sends a lower frequency. So, it can fight through, pipe corrosion and thick mortar linings better, maybe say than a transit time. But your ultimate decider will not be that, really the corrosion. It would be really, is it a good application for one or the other? And I do see where there's cases where both could be used. I've run into that, but I wouldn't make that really the decision on what you're banking on is whether, which one's better, with corrosive pipes. Do you have a timeline on the PTFM updates for use with the newer ANC sensors? Great question. And actually, the PTFM 1.0 is what you're working with now. So we will never add the ANC transducers to that. And the reason for that is we have a really exciting new development, and that is our new PTFM 6.1. And it's going to be miles ahead of the 1.0, the current portable. It's going to have the same diagnostic features. It's going to be able to handle A, B, and C transducers. It's going to have everything we have with the TTFM 6.1, except it's in a portable version. And that release date, I don't know the exact release date, but we're very close on it. And I suspect that will be done easily by the end of the year. Sometimes pipe thickness is unknown in the field. How far from reality will I be if I guess the pipe thickness? Another great question. And a lot of things can, as you know, can affect pipe thickness. Even off just brand new pipe can have variations. 6-inch schedule 40, it can be 6.065 or it can be 6.059. There's discrepancies there. So, sometimes that's what you have to do. You have to just guess, or if you can't get in and measure that pipe ID, or you could use a method. You could measure the pipe wall. There's some, there's different ways to do that. There's an ultrasonic ultrasonic tool that measures the thickness of the pipe wall if it's that important. But really, let's just say you have it. You say, I know it's 8-inch schedule 80 pipe, and you put in the numbers for that. You're okay. You generally will be okay. There's room for error on the spacing, but that you're dealing with reality. Some of these pipes just aren't what they say they are, or it's not what's in the drawing or whatever. And that's also where the diagnostic tools come in. So if I'm using, say, a transit time meter, a Doppler meter, I have things in my diagnostic menu that tell me, here's my signal strength, here's my signal confidence, and a lot of other factors that are in there. We can also read waveforms, for example. You can put in a USB, through a USB port, you can put in a thumb drive, and we can look at the waveforms. And those waveforms might indicate to us, maybe the spacing's off a little bit, or maybe there's a little bit of corrosion, or maybe this pipe wall is a little bit thicker than we think. So there are ways diagnostically to figure this out, but in terms of how far from reality you'll be, when you just consider the flow equation itself, it's just flow equals area times velocity. So however far off you're in the area is going to equate to a small error in your readings. Another question. I hope I'm not missing any here, that there's some above this. Sorry, let me scroll up a little bit. You guys are still waiting the agency approval on PTFM 6.1 to release. Are there other reasons why it's not already released? Can you confirm a release date for ATM PT 400 or PT 500 are the only portable solution for transit time on very small pipe? In terms of portables, that is correct. However, we do have we can go very small pipes on our TTFM 6.1. As far as waiting agency approval, that's not the issue. We are just working out firmware issues, doing some testing. We have beta models out, so we are working them. We do have a few out in the field. We just want to make sure everything's correct, the firmware is working, signal process is working, everything's good before we release it. So we're at that stage now. So it really isn't a matter of agency approvals. It's just getting the final testing done. Let's make sure I'm not missing anything here. Oh, see another new message. So the release of the PTFM 6.1, see, we are in September. I'd say very conservatively by the end of the year, and I'd be hoping for something sooner than that. Maybe late October, November. But I know we're close because I've actually seen one and I've got my hand on it. So we have the beta versions, like I said, and the release should be following shortly. I don't want to commit to something and get myself in trouble here. Oh, no problem. Glad to answer your questions. And let's go back to my Q&A, make sure I'm missing any there. Well, I hope I answered everything for you. A lot of good questions. And again, I really appreciate your time. Looks like we'll make it in just under the wire. But really, if you have anything else, we still have a few minutes. I'll wait you out. Oh, is there a hybrid version of the DFM and TTFM? Another good question. Not at the moment, but I can tell you it's something we're taking a serious look at. My experience with the hybrid, I've heard of hybrid versions in the field from other manufacturers, and where they are using for those of you that don't know what we mean by hybrid, it's a combination meter where you'll have applications. Let's take dredging, for example. You'll have a rush of clean water coming through a pipe. That's transit time technology. Then all of a sudden you'll get a whole bunch of mud and other junk. That's Doppler technology. It's a hybrid meter would be one that could detect both. And it would know when to switch from Doppler to transit time. The problem with the current hybrid meters out there are either the Doppler technology is not very sophisticated and it's just being used as a bridge until you can get to the transit time measurement. So it's giving you some reading. It might not be accurate, but just until it can get to the transit time measurement, it's using that bridge of the Doppler technology. The other thing with it is I think it takes a manual switch over. The one we're looking at that, and it's a ways up the road, but we are taking a serious, this is in R&D right now. It would happen seamlessly where we could do that switch over from Doppler to transit time when needed. So yes, we are looking at hybrid technology. It's just not available at the moment. Any other questions? Well, I'll hang out until this time's out. But again, I really appreciate everybody attending, taking time out of your day. And I hope this was useful for you. And just have a great rest of your week, folks.